All right, we're into section 2 of chapter 1, and we are going to talk a little bit about the idea of finding limits, but instead of finding limits right away in a traditional manner, we're going to start off by finding, which is by definition, we're going to find them first using the ideas of approaching it geometrically or graphically and numerically, perhaps creating a table of values, which is what I have to right off the begin, as you can see in the very first example. It says here, consider the function, if I could spell function that is, that's supposed to be an O there. Consider the function f of x equals x to the third minus 8 all over x minus 2 for x not equal to 2. But let's look at what happens to the function as x approaches. This means as x approaches 2. Doesn't equal 2, but it approaches 2. So I got my calculator out, and I plugged in some numbers here that are approaching 2 here from the left side are smaller values, 1.8, 1.9, 1.99, and here from the right side are values that are a little bit greater, 2.2, 2.1, 2.01. As you can see, these values are approaching 2 from the left side, from the right side. And notice what's happening to these y values. These y values are approaching what number? Well, based on the pattern, it sure looks like these numbers are approaching 11.9 and 12.01. Looks like it's approaching 12. So we would say that the limit as x approaches 2 of f of x equals 12. Now graphically, and hopefully you can be able to see that, I have the graph of this function, but I also have the graph of this function here with a different scale. Each one of the tick marks is worth 2. So as you can see here, as x approaches 2, I'm going to try to do this and go all the way on up. What does it approach? Well, it approaches 2, 4, 6, 8, 10, 12. As x approaches 2, y is approaching 12. So you can kind of tell from the graph as well. Now, this is not always the best way to determine a limit, but because right now of the limited, no pun intended, ways that we have, methods that we have to try to find this, this is going to work just fine. Now I'm going to say here, and this is written, the limit as x approaches 2 of our function f of x, which is this expression right here, is equal to 12. Okay. Now the idea again is what happens as x gets closer and what happens to the y value as x gets closer and closer to 2. All right. Now we can say that if f of x becomes arbitrarily close, arbitrarily, there's a good word, to a single number L as x approaches c from either side, from the left side, from the right side, we say the limit of f of x as x approaches c is L. Now this is a very informal definition. We're going to try to tighten this up just a little bit, but this is good enough for what we need, you know, for all our intent and purposes. Now let's go back to this particular function that I have up here. Do you see here that f of x is equal to x to the third minus 8 over x minus 2? Well, this actually simplifies. You can see here the x minus 2's are going to cancel, and I would have x squared plus 2x plus 4. Then it says as x approaches 2, my f of x would be 2 squared plus 2 times 2 plus 4, which again is 12. And that kind of backs it up. Now, I couldn't use by just plugging the number in here because I would get 0 in the denominator. But I have a function that's equivalent to this function. This guy here is equivalent to this function for all values except for x equals 2, which the function is not defined for. All right. Now, here's another good one. Let's consider the function, and this is one that you're going to see quite a bit, g of x, which is equal to the sine of x over x as x approaches 0. Well, we know that the sine of 0 is 0, but we can't divide by 0, so the idea of just plugging the number in isn't going to work. So again, I'm going to create a table, and while I'm creating the table, I'm going to clear off my first graph there, and I'm going to graph the second one here, which is the sine of x divided by x. And I'm going to probably have to change my window here just a little bit. So I'm going to go to my window here, and I'm going to, let's see here, go from, let's say, negative 6.28 to 6.28. That would be kind of like from negative 2 pi to 2 pi. And I'll make my scale 3.14, and then I'm going to go from, let's say, negative 2, that should be plenty, to positive 2, and I'll go by ones here. Now, in this case, as you can see here, I'm going to show you the graph in just a second, as g of x is equal to sine of x over x as x goes to 0, see how I'm getting closer to 0 from the left side, smaller numbers? It's approaching 0, and here positive numbers, but look what's going on here. These numbers are pretty close to 1 to begin with, but do you see how they're getting closer and closer to 1? So if I had to make a judgment call here, I would say that the limit of this function as x approaches 0 is equal to 1. Now, here we'll bring it over here, and let's go ahead and graph this and see what happens here. Hopefully I plugged. Oh, I bet I have this in degrees. Let me check my mode. Second quit here. Let me check my mode. Heavens, I do. Son of a gun. All right. Let's try that graph again here. There we go. And as you can see, as x approaches 0 from the left side or from the right side, now remember each one of these tick marks on the y-axis is worth 1. You can see it looks like it's going to go right up here to 0, 1, that the y value or the limit of our function would be equal to 1. And that matches up with what I have here. But I can't use direct substitution. I can't plug the zeros in because I would have an expression that's undefined. So finding limits can be a little tricky. We can do this using a table of values. We can use a graph to help us. And when we're lucky, maybe we can even use direct substitution. But what we need is something a little bit more formal than what we have here. Let me read this again. If f of x becomes arbitrarily close, if our function becomes close to a single number L, and you can tell it's a single number L because it's happy, it's not a married number, as x approaches C from either side, the limit of f of x as x approaches C is equal to L. That's a lot of thought right there. Okay, we're going to get a little bit more here. Let's see what happens now. Here's another function. F of x is equal to 1 when x is not equal to 2, and it's equal to 0 when x is equal to 2. Well, that's weird. It's equal to 1. My function is equal to 1 for every number except when x equals 2. So I'm going to graph this out. So it's not equal to 1 here, but it's equal to 1 for every other value. And then it's equal to 0 when x is 2. So now if I say, what is the limit as x approaches 2 of f of x? Well, what would that be? Is it equal to 0? Is it equal to 1? Remember, it's as x approaches 2. It doesn't say as x equals 2. So as it approaches 2 from the left side or from the right side, I'm at a y value of 1, which kind of shows you that the function doesn't even have to exist at this specific value of c. In this case, in this problem, c is 2. As x approaches c, as x approaches 2. So it does not even have to exist. Here it existed, it just wasn't a part of the horizontal line here. So we can do this numerically, we can do this graphically, and then pretty soon, that's not yet, but pretty soon we're going to be able to do this analytically as well. So there's 3 approaches to estimating limits. All right, now those are all our limits that existed. Let's see what happens when limits don't exist. Remember, the informal definition is f of x becomes arbitrarily close to a single number. A single number, can't be more than 1, can't be unbounded as x approaches c from either side. Okay, so let's consider this guy here. The limit as x approaches 1 of the absolute value of x minus 1 over x minus 1. Well, if that absolute value wasn't there, I would have x minus 1 over x minus 1. That would be equal to 1. But in this case, as x approaches 1, we have to consider what happens as x approaches 1 from the left side. So that'd be like 0.9 or 0.99 or 0.999. Well, if I plug in 0.9 or 0.99 or 0.999 in for x, down here I get a negative number, but up here I get a positive number. I get the opposites. So as the limit as x approaches 1 from the left side, I'm just going to write left side here for right now. This is going to, of our function f of x here, it's going to go to negative 1. But if we take the limit here as x approaches 1 from the right side, as numbers slightly bigger, like 1.1, 1.01, 1.0001, they're both going to be positive in the numerator and denominator. They're going to be the same exact number. So the limit is going to approach a positive 1. So in this case, we write DNE. It does not exist. Remember, it has to be a single number. It cannot be two different numbers. And that's the example of one that does not exist because the limit from the left side is not equal to the limit from the right side. Now in this case, this is a little bit different because it doesn't matter whether we're looking at negative numbers or positive numbers. We're going to raise it to an even exponent, so it's going to be positive. But as x gets closer and closer to 0, what happens here? Well, 1 over numbers that are getting closer and closer to 0 are getting bigger and bigger. 1 over 0.1, that's 10. 1 over 0.01, that's 100. 1 over 0.000001, that's a million. The smaller this gets, the closer it gets to 0, the bigger the value is. So this is unbounded. So it does not exist, DNE, because it's unbounded. Now you say, well, what would it help if I plugged in numbers and made a table? Absolutely, but I'm going to go ahead and, if I can bring it up fast enough, I'm going to show you a quick graph here. Of course, I have to maybe change my scale again, but I'm going to go for 1 divided by x to the 4th. I can put this in here quick enough, and then I'm going to make my window here. Well, let's see, we can go from negative 10 to 10 by 1s, but we're going to go from negative 2, or let's say negative, let's just go negative 2 to, let's go 100, or let's go 1,000, let's say, by 100ths. And if I graph this, you can see how my graph is climbing up. It's treating the x or the y-axis as an asymptote. It's never going to actually hit a value at 0. It's just going to get bigger and bigger and bigger. This is not a very good scale. I should have probably picked something maybe a little bit simpler. Let's see if I can try this one again. Let's go negative 2 to 2. And let's see if the graph makes it a little bit easier to see that now. Yeah, a little bit easier. You can see that it's unbounded. It's getting larger and larger and larger, and it's going to like a positive infinity idea. Now, so we can have a limit fail to exist if it's not a single limit. It has to be unique, or if it's unbounded. And this last one he's a strange guy, and you're definitely going to want to see the graph of this. What happens if we take the limit as x goes to 0 of the sine of 1 over x squared? So as x goes to 0, now we already know that 1 over x to the 4th gets bigger and bigger and bigger. Well, that's kind of what's happening here is I have 1 over the x going to 0. This number is getting bigger and bigger and bigger. Well, the sign of numbers, remember the sign is kind of a periodic curve. It's bouncing back and forth between negative 1 and 1. So since this is getting bigger without bound, my values are just bouncing back and forth between 1 and negative 1. So I don't have a unique limit. Now, you'll be able to better see this. And here are the x values if you go ahead and graph this yourself. So I'm going to go ahead and plug y equals. And I'm going to clear this out. And I'm going to write the sine of 1 divided by x squared. Sorry it's taking so long. I am just out of practice here with my graphs, and let's see here, and I'm going to do this one, and let's see what my last window was. It was from negative 2 to 2. Let's go here, use these values. So let's go from negative 0.25 to 0.25 by 0.05 for my scale, and then we'll go from negative 1.2 to 1.2, 0.2 being my scale again. And as you can see, I've got my window the way I want it, trying to make it look and agree with this. So now let's see what the graph looks like. Remember, here's my y equals. This is what I'm graphing. See how it bounces back and forth? And it gets just crazy there as we get closer and closer to 0, getting faster and faster and faster. So there is no unique limit because this thing oscillates back and forth between -1 and 1. So the limit does not exist. Those are the three main things. Now you have a special function. I think it's kind of an interesting one, named after a mathematician. And if you thought I would mispronounce the gentleman from the last section's name, you got to think that I don't have a chance on this one. So here we go. Listen to see how you pronounce this man's name. And this is a function that's named after him, which basically says that f of x is equal to 0 if x is a rational number, and f of x is equal to 1 if it's irrational. Now you know a little bit about rational and irrational numbers. They're not consecutive rational numbers. They're not consecutive irrational numbers. So you're going back and forth here. And of course, between any two numbers, there's an infinite number of numbers. So that makes it even a little bit more mind-blowing. But here we go.
Dirichlet.
Try it again.
Dirichlet.
Dirichlet. There's a name for you. Now, that particular function you won't come across unless you're doing an analysis class, maybe later on in graduate school. All right, so what we want to do is we want to take the informal definition. Here's the informal definition again. F of x becomes arbitrarily close to a singular number L as x approaches c from either side. We say that the limit of f of x as x approaches c is equal to L. And we write it in this manner right here. So what we're going to do is we're going to kind of fine-tune this a little bit, and we're going to use, of course, the work of mathematicians that came before us to make this a little bit easier. In fact, the particular mathematician that I'm speaking of, here is Augustin Louis, and then the last name here again. How do you pronounce that guy? Well, here we go.
Cauchy or Cauchy.
Sushi or Cauchy. There's a name for you. And it was this mathematician, I always pronounce it Cauchy. This mathematician formalized the definition of what we call now an epsilon delta definition. Now this little weird looking backward 3 and this thing that looks maybe like a note that you would see on your old piano music book, these are lowercase letter epsilon and delta. Remember, capital delta looked like a triangle, and we use these typically to represent small positive numbers. And what we're going to say here is, notice from the informal definition, f of x becomes arbitrarily close to L. That means the difference between f of x and L is a very small number. Now we're going to put absolute value so we can keep it less than a positive number, because we don't want some negative 1,000,000 or something like that. We want this to be a absolute value wise a very small number, smaller than a particular epsilon, a small positive number. Okay, this is going to be fun. And then it says here that f of x, of course, lies in this interval between L minus epsilon and L plus epsilon. X approaches c. This is also part of our informal definition. Means that, now by the way, if you've not seen this symbol, it means that there exists. This symbol means there exists a small positive number delta. This symbol means such that x lies in the interval between c minus delta and c, or c and c plus delta to either side, and we say that the absolute value of x minus c is between 0 and delta. It can't equal 0. It's got to be between 0 and delta, because remember, we are defining functions that don't even have to have a value at c. The function doesn't even have to be defined at c. So here is now the formal definition of a limit. As c and L, lowercase letter c and capital L, represent real numbers. The function f has limit L as x approaches c if for any positive number epsilon, we usually keep it to be a small positive number, there's a positive number delta such that for all x, 0 is less than the absolute value of x minus c is less than delta, implies that the absolute value of f of x minus L is less than epsilon. And we write this expression right here. And now you're probably thinking, oh no, there's no way I can understand this. I need to go back to the table or to just looking at the graph or hoping something algebraic works, like maybe something factors and cancels top and bottom. Well, the good news is that you're never going to have on the AP test, at least the AB version of the AP test, a problem where you have to use an epsilon delta proof to prove that this is a particular limit. However, you need to see at least one example in your life, and so I'm going to show you this example right now. It says, use the epsilon delta definition of a limit to prove that the limit as x approaches 4 of the expression 2x minus 1 is equal to 7. Now this would be like my c value, this would be my f of x, this would be my L here, that would all go back into this formal definition. So to show this, using the formal definition to show that for all, that means for all, it looks like an upside down capital A with the bar going a little further than the actual lines. For all epsilon greater than 0, there exists a delta greater than 0 such that the absolute value of my function 2x minus 1 minus 7, that's my limit, is less than epsilon whenever, and that's right here, 0 is less than x minus c, which is 4. X minus 4 is less than delta. Now that's what we're going to try to show. So we start with this part right here because we have to pick any epsilon that will make this true, and we have to find a delta that corresponds that will make it true. So for any epsilon, let's see, this is going to be less than epsilon, right? That's the definition. So we start with this. I'm going to go ahead and simplify the expression inside by combining like terms, then I factor out a 2. Now you remember that the absolute value of a times b is equal to the absolute value of a times the absolute value of b. So the absolute value of 2 times the quantity x minus 4 is the absolute value of 2 times the absolute value of x minus 4, which is, of course, the absolute value of 2 is 2, and this is less than epsilon. Now look right here. Do you see it coming? Do you see it coming? That's this part, if I can find it, I wrote it down, that's this part right here. So if I divide both sides by 2, I get that the absolute value of x minus 4 is less than epsilon minus 2. This is what I'm going to choose for my delta. So that means that if I pick delta to be epsilon minus 2, and I know that this is less than delta, which is epsilon minus 2, starting back here, that this expression here would be, oh goodness gracious, this is a 4 here. If I could write down stuff, I'd be okay. That 2 times the absolute value of x minus 4 is less than 2 times, remember I said that this is less than delta, which is epsilon over 2, which says that this is less than, where's my less than, there it is less than epsilon. So as I get closer and closer, now you can't hardly see it because it got cut off here a little bit, but as I get closer and closer to 4 here, and I can't even see my own self right here, as I get closer and closer to 4 here, you can see within this interval between 4 plus delta and 4 minus delta that my limit up here of 7 is in between 7 plus epsilon, 7 minus epsilon. It's all going to be within here, which means as I get closer, this gets closer. And that's the whole idea of the informal definition, and that is now our formal definition. Now if you're looking at that and you're saying, good goggly woggly, I'll never be able to memorize this. No, you don't have to. But I will tell you that if you take a college Calc 2 class, you're going to probably be responsible for doing some epsilon delta work. So it doesn't hurt to look through this, even though it's not going to be on your AP exam. The other thing that I can tell you is that my calc teacher, good old Dr. Ringenberg, was doing a proof much more complicated than this one. And he got stuck, and the class was just about to end, so he went ahead and dismissed us. Well, our next class meeting, he had handwritten out 35 of the actual proofs, the epsilon delta proof for the problem that he was working on. I don't know if the Xerox machine wasn't working, but he hand wrote them out, and I still have mine. And I've laminated it and keep it as a kind of a memento to my calculus days in college. All right, so good luck with this.